Hello everybody and welcome to today's lecture about differential protection. So let's first start with the load or external fault conditions. So we see here a protected object, which may be a cable, overhead line, generator or a transformer. And to the left side and to the right side of this protected object we have a set of current transformers, which transform the primary current into secondary values. Now let's see what happens if a current is flowing through. So the current enters the protected area on our left side and leaves it on the right side. And now let's see what happens to the secondary currents. The secondary currents are a replica of the primary current, and taking the polarity of the current transformers we see that the current that comes into the left side is transformed into a secondary current, which is the same as the one that leaves the object. So that means if we look at this connection point of the differential current measuring unit, we see that what goes in, leaves goes out. And now let's see what happens to the current differential sensing unit. The current that goes into the left side is the same as the one that leaves at the right side. So the difference is zero and we have the so-called restraint condition. So we have a very similar situation when we have an external fault. The difference is that the current is increased by maybe a factor of 10 or even more, but basically the polarity of the current, and so therefore the whole current situation, is more or less unchanged. So looking again on the summation point in this differential protection, we see what goes in leaves this point, so therefore we have no differential current and we have the restraint condition. A big difference is when we have an internal fault. So, in case of an internal fault, the faulty point has moved into the protected area, and now let's see how about the currents and their polarity. So, from the left side we have the current from source A, on the right side we have the current from source B, and these generate accordingly currents on the secondary side, which have opposed polarity. So when these meet at the sensing point of the differential current sensing unit, they add up and we have a trip condition. So differential protection appears to be a very simple thing, which is true in the sense that the principle is just related to Kirchhoff's law. But there are some flaws and they lead to the fact that we need some stabilization. For example, look in the details if we have a current flowing through a transformer. So we have a current that goes into the transformer and comes out after a little bit of the current has been deducted in order to magnetize the iron core. So if we have a current of 1000 amp leaving this transformer, then going back we need a current of 1002 amps or of 100.2 amps on the primary side to go into this object. And that means if we see what is the effect on the secondary side of these current transformers, we see that we have on the left side 1.002 amps and on the right side 1.00 amps. So the difference is 0.02 amps, which is very small, but it is a differential current. So here the remedy and remedial measure is to introduce the so-called stabilizing current, the restraint current, which is made up of the sum of both the incoming and the outgoing current, and this is compared to the release differential current. If the ratio is very small, then it is thought to be an inaccuracy and nothing happens. If it is large, then a trip occurs. So in this case, it was shown that the magnetizing current of a current transformer leads to some apparent differential current. So there are other sources for apparent differential currents that may appear in the operation of the protected object. For example, one is if we have a tap changing transformer where the ratio between the primary and the secondary side varies, then we have the higher the through current is, the bigger is the apparent differential current. So this is a straight line that goes up. Also, we can have in a transformer, due to the fact of saturation, a saturation differential current that comes up in heavy through fault conditions. All these add up to this S-shaped, an accuracy curve, and the differential protection should not pick up if we are below this curve. If we are above, then we have a severe fault and the trip must occur. This is done by installing a so-called band curve, which is made up of two lines, a horizontal one and a rising curve with a certain slope. In order to demonstrate this, I go back to the example of the magnetizing current of the transformer that we have seen before. So we have here the stabilizing current, which is 1.00 amps, and a very small differential current of 0.002, and as we can see, the blue dot is below the trip curve and the protection is stable. So this was today's lecture about differential protection.